All right, welcome back to linear algebra. Let's jump into Anki to begin with. What is the difference between the comma delimited form and the comma vector form of a vector v in Rn? Comma delimited form is kind of in that form of like parenthesis s1, s2, sn parenthesis versus column vector form is basically column vector matrix with the same values. What is the pivot positions? What are the pivot positions of a matrix? Pivot positions are the locations of the leading ones in the reduced row echelon forms of the matrix. What are the standard basis vectors in Rn? Basically, E1 is 1, 0, 0, dot, 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 0. E2 is 0, 1, 0, dot, 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 0. E3 is 0, 0, 1, dot, 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 0. And then En is 0, 0, 0, dot, 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 1. What is a vector in Rn? A vector in Rn is I don't know, how do you define that? It's a set of real numbers. It's an n tuple of real numbers. Boom, got it. All right. Now what I'm gonna do is grade what I did yesterday, and then we'll go from there. All right, got them all right from yesterday, so I'm gonna continue working on more practice problems now. All right, so basically I restarted that proof today. The proof is essentially trying to show that if the transformation A and transformation B are matrix transformations and commute, then they commute if and only if A and B commute. And so to show that that statement is true, we need to basically show two things. We need to show that if transformation A and transformation B are matrix transformations and commute, then A and B commute. And we need to show that if A and B commute, then the transformations A and B commute. And so that's the first part. So the first one is showing that if transformations A and B are matrix transformations and commute, then A and B commute. And so by definition, this was just me thinking through this. By definition, transformation A and B, transformation A and transformation B commute if transformation A, O, transformation B equals transformation B, O, transformation A. And if transformation A and transformation B commute, then okay, we already said that. Actually, no, by definition, A and B commute if AB equals BA. So here's the definitions of what it means for them to commute. Then I say, if transformation A and transformation B commute, then TAO, TB, and TBO, TA. That's basically the definition. And then you say, TAO, TB equals TAB, and TBOTA equals TBA. Okay? And this is by theorem 1.9.1. That's important. That's important. Because then, therefore, TAB equals TBA basically by substitution of these into this. And then if TAB is a matrix transformation, then TAB can be represented as ABX equals B by definition. Following this, TBA can be represented as BAX equals B by substitution. ABX equals BAX. Multiplying both sides on the right by the inverse of X, we get that AB equals BA. Therefore, transformation A and transformation B are matrix transformations and commute. If that's true, then A and B commute. So these proofs are always difficult for me because I've never really learned how to do proofs other than watching like one 45-minute video. But maybe that's a good thing for learning, that they are difficult and uncomfortable. Anyway, we need to show tomorrow that the other way is also true. If A and B commute, then TA and TB commute. So that's what I'll work on tomorrow. So that's it for today. Talk to you tomorrow. See you.